Hey everybody, in this video we are going to be working on example 3 in section 5 of chapter 1. Chapter 1, Equations and Inequalities. Section 5, Applications and Modeling with Quadratic Equations. These are all on one collected playlist. This is an Algebra 2 course. Height of a projected object is the theme of the word problem we are looking at. A little note about height of a projected object, and this is going to be true through algebra, pre-calculus, calculus, and this also overlaps physics, although in physics you typically use meters per second, and in math class we tend to use feet per second. All right. This says if air resistance is neglected, the height S in feet, we use height as S or position in feet of an object projected directly upward from an initial height of S sub 0 feet. Now, S naught or S sub 0 means naught, means like nothing, S sub with nothing for time. No time has passed, therefore initial height. Initially, no time has passed, right? With an initial velocity of V naught or V sub 0, not like NAUT, by the way. V sub 0, so that's the velocity upon release of this object that's being fired up or dropped or whatever. V sub 0 in feet per second is given, and velocity is like speed, except velocity has direction. So positive means up or to the right, and negative means down or to the left, depending on the context of the problem. Is given by the following equation: S position equals negative 16 t squared plus initial velocity times time plus initial height. Here, t represents the number of seconds after the object is projected. This equation is the same for every math class you're going to take from now on. So you might as well just memorize it and recognize it whenever it pops up. It's all over the place. Pops up, projects up. Here, t represents the number of seconds after the object is projected. I kind of cut it off a little. The coefficient of t squared, negative 16, is a constant based on the gravitational force of Earth. Acceleration due to gravity is negative 32 feet per second squared. So really you'll understand why in the future, but you would divide that number by 2 to work its way backwards into the position equation from position to velocity to acceleration. So you would multiply it by 2, or divide it by 2 rather. So that's why we have a negative 16 and not a negative 32. So in physics, you probably do 1/2 acceleration somewhere else as well. I think you have like 4.9 or 9.8, right? Don't you guys have something with that? It's been a while since I've done a physics style question, but whatever it is in meters per second squared. The constant varies on other surfaces, such as the moon and other planets. So that leading coefficient, negative 16, will be different if it was on Mars, on the moon, wherever, okay? So let's get into the word problem. So here we go. Let's go right there. If a projectile is launched vertically upward from the ground with an initial velocity of 100 feet per second, neglecting air resistance, its height S in feet above the ground t seconds after projection is given by S equals negative 16 t squared plus 100 t. I'm just going to pretend, I'm going to erase it in a second and pretend if we had to write that equation ourselves, talk you through it because that's likely going to happen. And then we're being asked 2 questions. After how many seconds will it be 50 feet above the ground? And then the next question, how long will it take for the projectile to return to the ground? So first thing, how do we write this equation ourselves if it were not given to us? So first thing is, oops, I shut my pen off. Hello. Oh, too big. Okay. So what if we had to write the equation ourselves? Okay. So we said it's going to be S, and I might even say S of t, like f of x, right? Equals negative 16 t squared always, plus initial velocity times time. So upward, positive 100 t, plus the initial height will go here. From the ground is the detail. So since it's from the ground, its height is 0. And that's why the equation that was given to us didn't have a value there. And really, it was just focused on this part, right? Because we don't need to write plus 0. That's silly, okay? After how many seconds? So that means we're figuring out what t will be. Will it be 50 feet above the ground? So let's even envision what the graph, the visual of this would look like. So t is our input. It goes on our x-axis. S is our output height. It's on our y-axis. This object starts on the ground, and over time, it'll go up, hit a max height, and then start falling down and hit the ground. Now, it's possible it's 50 feet above the ground twice. It's possible it's 50 feet above the ground once if that was the maximum height. And it's possible it's never 50 feet above the ground because the highest height it gets to is 49 feet, 38 feet, whatever. So we need to figure that out. So we're going to be solving for time. And I know that 50 feet above the ground, that means either if it's set up the way the book set it up, S is equal to 50, or in the case of how I wrote it, S of t equals 50. Either way, the position or the height is 50, and we're going to solve for time. And like all polynomial equations, we're going to get it equal to 0 before we can solve, right? So let's go from there. That'll be 50 equals negative 16 t squared plus 100t. Get it equal to 0. I'm actually going to opt to bring everything to the left side so that I'm working with positive coefficients in front, but it's not really going to matter because, spoiler alert, this one's not factorable. We need the quadratic formula. But 16t squared, positive, right, minus 100t plus 50 is 0. Now, even if you're using quadratic formula, there's no reason why we can't divide everything by 2. And if you brought everything to negative 16t squared side, you could divide everything by negative 2. So if I divide everything by 2, 8t squared minus 50t plus 25. Now 8 times 25 is 200. What multiplies to 200 and adds or subtracts to give you 50? Again, spoiler alert, you can't find anything, okay? It's not going to work nicely. So that means we're going to use the quadratic formula. So from here, x equals negative b, so that's going to be positive 50 plus and minus the square root of b squared, 50 times 50, 2500, minus, I don't think I'm going to fit, 4 AC. Well, AC we already said was 200. So times 4, that's not so bad, 800. Okay, I can fit this. All over, do not make that fraction bar go across the equal sign. 2a, which is 2 times 8, which is 16. 2,500 minus 800, 1,700. So x equals 50 plus minus the square root of, the square root's a little aggressive, yeah? Okay, now if I grab my handy dandy calculator and I figure out what's the square root of 1,700 is, do I have the calculator out? I don't know. Okay, let's see. 1700. Take the square root. I get 41.23. So that right there is about 41.23, right? I'm going to do 50. I just want to clarify this because people do weird things, right? So to get two answers because it looks like I'm getting a positive. This is the discriminant, right? Getting a positive number under the discriminant. I'm going to get two real answers. So that means I'm probably like this situation where 50 is not the max height, right? I'm going to pass through 50 on my way up. I'm going to pass through 50 on my way down. So really to get the two decimals, you're going to do 50 plus whatever, 41.23 and divided by 16, you're going to get an answer from that. I guess we could put squiggle equals approximate, and then x will equal 50 minus 41.23-ish over 16, and we're going to get a smaller answer in this case. So I'll get x is approximately equal to what? So what are those two answers? So x will be, all right, actually, if we're going to be precise, I'm going to be a typical myself over here. X, it's not really X in the problem, it's T, right? Because we're solving for time. And I don't want to lose track of what it is we should be focused on, right? So T equals T. All right. So from there, my bigger answer, when all is said and done, if you want to pause and try it in the calculator yourself, about 5.70 seconds. That's going to be on the way down. And my smaller answer is 0. Really quick, 0.55 seconds. That's going to be obviously on the way up, right? So here in this picture, this is 0.55 seconds. And this one was 7 seconds. So here again, 0.55 seconds, 5.7 seconds. If I find the midpoint of those two times, because parabolas are symmetric and parabolas come from x squared, or in this case, t squared, I can find when the vertex is by finding the midpoint of those two values if I was so inclined, right? So I have at two different times. And there you go. So that's the answer to part A right there. Next, how long will it take for the projectile to return to the ground? So what do I know about this projectile when it's on the ground? When the projectile is on the ground, if I'm looking for how long will it take? Well, that means I'm solving for t again. That means I need to know s equals something so I can solve for t, right? That means I need to solve for what s equals, or need to know what s equals from the information so I can figure out the value of t. Well, if it's on the ground, s equals 0 when it's on the ground. So 0 equals, so that's going in for our position or height. 0 equals negative 16t squared plus 100t. And that's it. It's already equal to 0, so now we could solve. 0 equals, what can I factor out? How about a negative 4t for my GCF? That leaves me with 4t minus 25 on the inside. Zero product property. I'm going to get t equal to 0 from that guy right there, right? And then I will get 4t minus 25 is 0. So add 25 and divide by 4. Half of 25 is 12.5. Then half of 12 is 6. Half of 0.5 is 0.25. So 6.25 seconds. So again, one is on the way up and one is on the way down. When is it on the ground? It's on the ground at 0 and at 6.25 seconds as well. Doesn't that make sense with 0.55 seconds after takeoff? And then 5.7 seconds right there. Now, if it took 0.55 seconds for me to get to 50 feet above the ground, it will take 0.55 seconds to get there again. So if you have 5.7 as when it was 55 feet above the ground or 50 feet above the ground, and you add 0.55 to that, we get, so 0.3 gets us to 6, and we still have 0.25, so 6.25, there you go. So you get 6.25 that way as well, but obviously that's not using um, the polynomial equation. That's using a little cheap trick, but you can't always use that in every kind of calculus style question, right? It's just, it happens to work out in this case. So you always want to know technique. So there you go. So the answer for part B was, how did they word the question? How long will it take? It will take 6.25 seconds before hitting the ground. Sometimes instead of saying hitting the ground, it'll say like what's the time of impact, something like that. So you gotta kind of read between the lines sometimes, right? And know what the question is. Oops. And go from there. So I hope you found this video helpful if you're doing a projectile motion problem. That's it. Check the playlist, give a thumbs up, give me a comment or some requests in the comment section. I see those right away if I'm uploading, so I could jump to it. So if you see I just uploaded this a few minutes ago, chances are I have my YouTube open. I'm recording and uploading as I sit here. So just leave a comment if you want me to do a video in this moment, okay? That's it for now. Adios. Bye.